Hello, everyone. Welcome back. We are going to be doing chapter 5 today, and starting chapter 5, I should say. And we will be talking about discrete functions, discrete probability distributions, I should say. And we're going to start. So, by the way, this is our first probability distribution that we're going to be doing. And although most of our probability distributions are going to be continuous, chapter 5 is all about the discrete, and 5.1, which is actually section 5.2 in your textbook, even though it says part 1. And we're going to jump into it. So let's start with some definitions. We're going to start with a random variable. This variable, typically represented by a capital X, that has a single numerical value determined by chance for each outcome in a probability experiment. We will be using this throughout this video and the next one, actually for many more to come. And the probability distribution of a discrete random variable X provides values of the random variable and their corresponding probabilities. This can be done in the form of a table graph or formula. And random variables are going to be either discrete or continuous. And like I said, for this particular video, and the rest of chapter 5 will all be discrete. And then from after chapter 5, from chapter 6 on, everything will be continuous. So here are some rules. Let P of X denote the probability of a random variable X equals a specific value, lowercase x. We'll run into that later. The sum of all of the probabilities must equal 1. That's sort of a good way that we can make sure that we have all of the probabilities is when we add them up, we get exactly 1. And each probability value must be between 0 and 1 inclusive. And once again, the inclusive means that we are including 0 and 1. And what that means for us is a probability of 0 means that it is impossible for an event to happen. And a probability of 1 or 100% means that it's a 100% guarantee. There's no chance of it not being that. So let's demonstrate this with an example. Let a random variable X represent the number of heads in 3 tosses of a fair coin. And we're going to construct a probability distribution. Well, I have several possibilities. It's possible that when I toss a coin 3 times, I get 0 heads, or I get 1 head, or I get 2 heads, or all 3 of them come up heads. And this is it. This is our only set that we have here. And I want to do a little table for us, a little diagram here. My first toss is going to be heads or tails. The second toss will be heads or tails. And the third toss is either going to be heads or tails. And I'm going to write these out. So we have 3 heads, 2 heads and a tail, head, then tail, then heads again, or a head and 2 tails. We also have tail, 2 heads, tail, heads, and a tails, tail, then a tail, then a heads, and 3 tails. And this is my entire sample space. This is it. And to be clear, and in this case, is 8. So that's going to be my denominator for my probabilities each time. Now, let's start with, what's the probability of getting 0 heads? Well, there's only one chance of me getting no heads. So that means there's one chance out of the 8. How about getting one head? Exactly one head. Well, we have this here. We have this here. And we have this here. So it looks like we have 3 chances out of the 8 of getting exactly one head. How about getting 2 heads? Exactly 2 heads. We have here. We have here. And we have here. So again, it looks like we have 3 out of the 8 chances of getting 2 heads. And getting 3 heads, we only have 1 option left. And that is here. And what we can do to verify that we have the entire set here is when I add up my probabilities, you'll notice I get 8 out of 8 heads or exactly 1, which again was part of the criteria. When I add them up, I should get exactly 1, and I do. All right, we are now going to multiply across. You see at the top there, that last column, it says x times p of x. So here I'm going to have 0 times 1/8, which is 0. Here I'm going to have 1 times 3/8, which is 3/8. Here I have 2 times 3/8, 6/8. And I know I can reduce that, but I'm not going to because I want to keep the denominators the same. Then I have 3 times 1/8, which is 3/8. And now we're going to add all those up, and this is going to give us 3 plus 6 is 9, plus 3 is 12. This is going to give us 12 over 8, which is exactly 1.5. And this is what we are looking for. This is what we refer to as the expected value. And we could also say it's the mean. Okay, so what is this? What is the meaning of this? How do we get some information out of this? Let's say I were to flip a coin 3 times and record the number of heads, but I were to do this 3-coin toss. I would repeat the experiment 100,000 times. I would expect, on average, I would have about 1.5 heads, meaning I'll never have exactly 1.5 heads. However, we can see, based on the probabilities here, that 1.5 is right in the middle between 1 and 2, meaning most of the time I'm going to have 1 head, or I'm going to have 2 heads. There'll be times when I have the other, the 0 and the 3. But on average, we can see the highest probability is the 1 head and 2 heads. And so right in the middle makes sense for it to be the expected value. So let's do some more with expected value. And here is a formalized formula for what we just did to find the expected value, this one here. There's that x times p of x. And this is how we find the expected value, or the mean. So let's go through another example. A lab orders a certain bacteria culture each week, 52 weeks a year. The price for each culture weekly follow the distribution below. And I want to interpret this table here. This is saying that 20% of the weeks, it only costs $10. 30% of the weeks, it costs $12.50. And half the weeks, or 50% of the weeks, it costs $15. And we want to know, on average, what would we expect to any given week to cost? Well, our expected value is going to be the probability times the price plus the probability times the price plus the probability times the price. Now, just guessing, I'm going to guess that it's going to be somewhere between $12.50 and $15.50 as far as an average goes. Using my trusty calculator here. And I'm getting, on average, I would expect on any given week it to cost about $13.25. as our expected value. Now, the next question, again, which makes sense. So we kind of hypothesized that it'd be probably something between $12.50 and $15, which makes sense since the higher probability is definitely in those two categories. Now it says, how much should the lab budget for the next year's shipments? Well, if it's $13.25, and I should really emphasize this is per week, should be definitely part of the answer. Well, then that means I'm going to have to multiply the $13.25 times 52, the number of weeks in a given year, times 52. So how much should we budget for this? $689. And if I was doing the budgeting, I would most likely round that off to $700. But we can see we made each week about the same price, even though sometimes it's above and sometimes it's below. And then times 52 gives us a good idea of what we would expect to have to budget for that particular cost. All right, let's do another one. Suppose a life insurance company sells a $120,000 one-term life insurance policy to an 18-year-old female for $150. I want to explain what that means. This means that there's an 18-year-old female who wants life insurance, so she buys a life insurance policy for $150. If she dies during that time, her benefactors would end up with $120,000. Now, the probability that the female survives the year is 0.999356. Now, that probability right there, the insurance companies pay a lot of money to get that as exact as they possibly can so that they can optimize their pricing as well as their profits. Compute and interpret the expected value of this policy to the insurance company if the life insurance company sold 12,000 of these policies for a given year. All right, we are going to take this from the perspective of we are the insurance company. So if she lives, we get to keep the $150 that she paid us. Now, if she dies, and I want to be clear here, they don't get $120,000. They get $120,000 minus the 150 that they put in, because it's kind of like they're giving the money back to the person. So we say that she's down $119,850. Meaning we're down. As the insurance company, that's a negative for us. All right. What's the probability that she lives? Well, they give that to us. All right, now what's the probability that she dies? So I'm going to write this over here. Probability that she dies is going to be the opposite of the probability that she lives. Now, I want to make sort of a point here. My calculator says 0.000644. It's possible that your calculator instead says 6.44 with an E and then a -4. If it says that, that means the same thing. This technically means that this is 6.44 times 10 to the -4th power, meaning you need to move that decimal 1, 2, 3, 4 spaces and fill in the zeros, is what that means. So you may need to manually write that out with the zeros in there. All right, so we have that. And I'd like to point out the summation of the probabilities is 1, as it should be. I'm now going to multiply across 150 times 0.999356 and negative 119,850 times 0.000644. And I'm going to add that number to the 149.9034. And this is giving us this. And that is our expected value for each policy. Let's interpret what we mean by this. And this is expected value. Meaning, we give lots of these insurance policies out, or sell for $150. And most of the time, these women live. So we're just collecting $150 from each one. On very rare occasion, an 18-year-old woman would die. Now, when that happens, we have to pay a lot of money out. So on average, how much would we say each policy is worth? We're making about $72.72 on each of these policies. And this is per female. Now, the last part of the question says, if the life insurance company sold 12,000 of these policies for a given year, how much money can they expect to make? Well, I'm going to take 7272, multiply that times 12,000. So that's going to be about $872,640 in a given year. Now, and although that sounds like a lot of money to you and me, to an insurance company, it's really not that much money. They're making billions and billions of dollars. All right. Interesting stuff. Let's do another one. When you buy one ticket out of for $1 out of a lottery of 1,000 tickets, where the prize for the one winning ticket is to be $500, what is your expected value? We're now playing as the person playing this game. So we'll start here. If I lose, I'm out $1. However, if I win, then I get to make $499. Now remember, that's the $500 minus one, because they're just giving me my dollar back. What's the probability of losing? Really high. 999 out of 1,000. And the probability of winning is 1 out of 1,000. And again, please note, when I total these probabilities, I get 1,000 over 1,000, or once again, a 1. All right, I'm going to multiply across. -1 times 999 over 1,000 is negative 999 over 1,000. 499 times 1 over 1,000 is 499 over 1,000. When I add those together, I get negative 500 over 1,000. And here is my expected value. Meaning most of the time I'm going to lose, and on rare occasion I'm going to win. So if I play this lottery maybe 100,000 times in a row, I'll win occasionally, but I'll mostly lose. So on average, we would say that we're down 50 cents overall is the expected value. All right, next up, we have some problems from ALEKS. Data from the latest census show that households in Oaktown have 0 to 5 children. Suppose that a household in Oaktown is randomly selected. Let X be the number of children living in that household, and here's the probability distribution of X. So let's interpret this table here. This says what percent of these households have no children? 19%. What percentage of these households have one child? 24%. Two children, 28%, and so on. And you'll notice not very many have 4 or 5 children. The bulk of it is going to be 0 children, 1 child, or 2 children. All right. So let's look at part A. So parts A and B below, find the probability that the randomly selected household has a number of children described. Less than 3 children. So less than 3 is here. So that's looking to me like 0.19 plus 0.24 plus 0.28. It looks like we're looking at about 71% have less than 3 children. Next up, we have no less than 3 children. So now we're looking exactly here. So 0.16 plus 0.09 plus 0.04. Notice that this part B is actually the complement of part A. I could have done 1 minus 0.71 and got the 0.29. But these are my 2 examples. So I'm hoping we can see this really isn't that difficult to do. All right, next up. A charity is running an auction. 1,000 tickets are sold at $2 each, and we have numerous prizes here. We have 8 prizes of $100. We have 8 prizes of $50. We have 8 prizes of $25, and we have 8 prizes of $10. So that's a total of, that's 32 prizes total. And we're going to start here. So if we lose, then I'm out $2. What's the probability of me losing? Well, I'm going to go over here real quick, and I'm going to do 1,000 minus the 32 to get 968. This is the number. This is losers. So that means that I have 968 out of 1,000 chances of losing. That's really high probability that I'm going to lose. Let's go to the table. Now, let's say I win one of the $10 prizes. Well, in actuality, I've actually only won $8 because remember, it cost me $2 to get in. The probability of getting that's going to be 8 out of 1,000 because there's 8 $10 prizes. If I win $25, I've actually only won $23. And once again, I have a chance 8 out of 1,000 to win the $25 prize. To win the $50 prize, I actually am only making $48. And the probability, again, is going to be 8 out of 1,000. And winning $100 is actually only $98. And again, I have 8 out of 1,000 chances of winning that. So we are now going to find the expected value. So our expected value would be -2 times 968 out of 1,000 plus 8 times 8 over 1,000 plus 23 times 8 out of 1,000 plus 48 and 8 out of 1,000 chances of getting that plus 98. And I'm going to only focus on the numerators for now because the denominator is 1,000. We already know that. So negative 2 times 968 plus 8 times 8 plus 23 times 8 plus 48 times 8 plus 98 times 8. There's my numerator. The denominator for all of them is 1,000. And when I divide that out, I get negative 0.52. And that is not looking good. Here's our expected value. We're going to be down 52 cents on average. I hope you found this helpful.